We've talked about deriving Lagrange equations. We got there from eliminating the forces of constraint. We then talked about what Lagrange equations look like in the context of conservative forces, which we indicated was kind of the general context in physics. Anything that's not conservative is only not conservative because we're not looking closely enough at it. So, in a sense, these are the equations of motion that we're going to always worry about. Now, we are taking ourselves along a tour, and we have stopped when we derive these equations at a little side town called Lagrange equations for conservative forces. And before we leave the town, let's look at some of the historical artifacts. And these are the indications as to what a conservative force really is. Now, we first have to define a conservative force and then consider all the different properties that it has before we can truly understand it, before we can truly derive potential functions. That's what we're going to do today. If we get far enough, we'll then move on to the Lagrange equations for systems. In the tutorial today, we will derive potential functions for conservative forces. And then, I will at some point over the weekend upload a quiz. We've been missing those, right? A quiz due at the end of next week, basically about everything up till this point. So I'll put a little question in on Newton's laws, I'll put a little question in on Lagrange's equations, I'll put a couple of questions in on some actual solved problems from the tutorials. So it's a good plan to post from the tutorial so that you can know the answers. And there will be questions on conservative forces. And that's will be it, right? So that's where the quiz will go out. So nice little thing to make sure that we're not losing any class. Let's now move on and talk about conservative forces. So a force is conservative by definition. A force is conservative if we can write it as negative gradient of some potential function. Force can be written as the negative gradient of some potential function. Now we're going to take this and we're going to prise it open and look at all the implications. Most of you, if not all of you, have done a multivariable calculus course in which you've probably seen some of these ideas. So we're not going to be too detailed. What we're just going to emphasize is the concepts. And they are important concepts. The meaning of conservative force. So I'm going to start with a seemingly quite basic one. And it's the notion of path independence. Now we all know what work is. A force does work by moving the system from one place to another. The amount of work that is done is going to be proportional to, over some small displacement, is going to be proportional to the force in the direction of that small displacement. I just said in the written equations like this. Yeah, we've seen this earlier, right? And we know that to get the work, when we move from one place to another, we simply integrate this. So the work in moving from one place to another is simply the integral from place 1 to place 2 of f dot. Now, what do I mean when I say from place 1 to place 2? I'm going to reason for the moment about a particle in space. All of these ideas apply equally well to systems in configuration space, where configuration space is some manifold parameterized by our generalized coordinates. But let's speak about a particle in space. It's living at a certain point. And then we move it. We move it along some path to a certain other point. And we move it by applying some force to it. When we ask the question, what is the work done by the force? We ask, well, the particle may have had other forces applied to it. The work done by my force is at each section of time, the components of that force along the trajectory of the particle added up, integrated, over the entire trajectory to give me a value, a number called work. And if I moved the particle along some other trajectory, I would have integrated along that other trajectory. So instead, I'd move the particle in another way. I would integrate now over that path. Right? And I would find the value of the work done by the force as I moved along this other path. Now, a force is called path independent if no matter which path the particle moves from here, point A, to here, point B, it does the exact same work. But you repeat, no matter which path the particle moves from point A to point B, the force does the exact same work on the particle. Then the force is called path independent. That makes sense. No matter how I move it from here to here, it's path independent. As an example, let's talk about the force of gravity. If I take an object that I don't mind throwing on the floor, this bottle, and I drop it directly downwards, gravity does a certain amount of work on it. The work that it takes to bring it from here down to there. Now, if instead of dropping it directly downwards, I buffet it from side to side, I'm swinging it with my arm or whatever, now I allow it to throw it up and down, and I'm doing a whole bunch of motions with it, and then eventually I get it all to the exact same point. From the beginning of all that crazy motion to the end of all that crazy motion, gravity's done the same work. So, this and this. From here to here, gravity did the same work, even though it followed a completely different trajectory. It started and ended in the same places. And gravity did the same work. We'll prove that. Gravity is a conservative force. And gravity is the work done by gravity is independent of the path traveled by the object, provided we know where it starts and where it ends up. Okay, that's called path independence. So we have two concepts here. Path independence, no matter which way I move it, as long as it starts here and ends here, the force does the same work. Conservative, the force can be written as the gradient of a potential function. Which one's more intuitive? Which one do you immediately understand? Path independence. This one is obscure and weird. Alright, but which one's easier to deal with mathematically? This one. Okay, so we've got two sides of something. Now we need to show that they're the same thing. That's what we're going to do next. So that we can reason intuitively very nicely about something, and yet also mathematically, and it's in fact the same thing. Conservative, if and only if, path independent. Well, we make big claims, we better be prepared to do big maths. Let's prove that these two are equivalent. That in fact, conservative and path independent are the same thing. That we can reason about something that is a gradient of a potential function by saying the work done from place to place is in fact independent of the path traveled. To prove equivalence, You have to prove that if you assume this one, it means this. You also have to prove that if you assume this, it means this. So we'll start by going in the forwards direction. We'll start by proving that if I can write the force as the gradient of some potential function, then indeed that force is path independent. How are we going to do that? Well, I'm going to choose a path. A path RT from A to B. Right. This path starts at point A, goes along some trajectory, ends at point B, and at each time value along the path, the position here is given by R. Right. So I don't know how you'd write it in pure maths. So I think you'd probably write something like path is RT, where T is an element of T naught, TF. Something like that, right? This is unimportant. We've got a path RT from A to B. Now we want to show that no matter what this path is, only the fact that it goes from A to B is important for the work done. Right. So what is the work done? The work done from A to B is going to be the integral, right, of the force dot dr as I move from A to B. Now remember that I can write the force by my little mathematical thing as the minus gradient of the potential. This is minus the integral from A to B of gradient potential dot R. Okay? Now I'm going to write this out as a proper path integral. So I'm going to write this out as a proper path integral. When I write this out as a proper path integral, it looks like the integral the integral from time naught to time at the end, right, of this, of R of T, right, dot dr dt, right, and dt. Right, so that's my path integral. Assuming, of course, that we're evaluating this one also at each t value. Right. So the next thing I want to do is I want to imagine, okay, I'm not going to, I want to imagine that I have previously defined a function. I'm going to do it somewhere else so that you can see clearly that this is ongoing. So, keep that in mind. Let's define h, some function, some scalar function of time, to be u. No, it's not v, it's u. That's what we call a potential function. U at r of t. Alright, so that's just normal construction. H as a function of time gives me the potential at the position at that time. Nothing fancy, no black magic. Let's work out the derivative of h. We use the chain rule to work out the derivative of h, right? The chain rule tells us that the derivative of h, variously, depends how you want to do it. How should we do it? Let's do it stepwise and then come up with a nice expression. So it's partial derivative of u with respect to x1 or q1, whatever variable is the first variable in R of t, right? Let's use x1 times the x1 by dt plus partial derivative of u by del x2 the x2 dt. This is the chain rule. We've been using this guy. Partial derivative of u dxn dxn dt. Yeah, so far so good. we can write this as a dot product of two vectors, right? This looks like the dot product of two vectors. This looks like the dot product of del u, del x1, del u, del x2, del u, del xn, dotted with something that looks like dx1 dot times dt, dx2 by dt, dxn dt. Okay, what's this vector commonly known as? Grad u. Grad u dot, what's this vector? dr dt. This is d of everything by dt. d by dt of x1, x2 to xn. Okay, that's interesting. Why is that interesting? What have we got upstairs? We've got the integral of grad u dot dr dt. Grad u dot dr dt. Same thing. But that's just the derivative of this h of t. This ordinary function, h of t. Right? So let's do that. Let's go back upstairs and let's rewrite what we've got up there in terms of what we've got here. Is equal to the integral minus the integral from t0 to tf. This is simply h prime of t. There's a thing called the fundamental theorem of closure. I've been shouting that word at you a lot. It's like a square word already, the amount of times I've said it. FTC. If you differentiate something that is, if you integrate something that is the derivative of some function, you just get the function evaluated at each of the endpoints. So this is simply equal to h of tf minus, oh wait, there's a minus outside. That'll make you reverse everything, right? That's the minus here. So it's h of t0 then, okay? t0 minus h of tf. Okay, so what was h of t again? H of t was u of r of t. So this is simply equal to u of r at t0, the place we started, r0, minus u of r, the place we finished, rf. But r0 is a and rf is b. That's how we parameterize this. We said we start at a, we end at b, and we go along some path. Alright, so this is simply u of a minus u b. Okay, do you see the path anywhere there? No expression for path. So the work done is u at the one endpoint minus u at the other endpoint. And every little description of the path, whatever r of t was to get from one to the other, has vanished. It's disappeared. So what have we shown? We've shown that this force is in fact path independent. We've shown that when we take a force that is conservative, then we work out the work done when we move from A to B along any path, we get some value only dependent on A and B, and independent of what we did in between. Only dependent on starting position and ending position, and independent. Now we got this. Right. So we've done one part of the proof. What's left is to complete it. If I tell you that something is path independent, then it better also be true that it is conservative. Let's prove it. Now prove the opposite direction. Take out my angle. We now prove the opposite direction. We have to start now with path independence. And we have to show that in fact when some force is independent in path, then we can construct a potential function u. We're going to do in this tutorial, we're going to be constructing potential functions for specific forces. But let's now show in general that it can be done. Alright, so let F be path independent. Now we have to show that the work done by F is independent of the path that we move it at. We know that, but we have to show that we can find some function u such that F is equal to the gradient of u. What we do is the following. We start at A, we know we're going to B. Right? Now, in order to do this, I choose some point near B, and there is an implicit assumption here that I can always find an open ball around B inside the set I'm considering. The set on which F is defined. The manifold. In other words, the assumption for those of you who are doing Maths 3 is that the manifold is open region. So I can find some little piece around B, right? And I choose something like that. Okay. And let's call this point P. So I've gone only along the x direction from B to B. Now I'm going to choose any path, doesn't matter which path, from A to P. Why doesn't it matter which path? Because F is path independent, right? So the work done by the force from A to P is dependent only on A and P as vectors, right? It's not dependent on anything else. And then I do the integral, so the work done at some value. So the work, let's say, from A to B is equal to the work from A to P plus the work from P to B. So that's the work from here to here. I can choose a path because it's path independent. And for this last section, it's along a line. So I can write that out. This is equal to the work from A to P, which is only a function of A and B, plus this part here is a line integral. So I parameterize it. Integral, how do you do a line integral? It's going at the height here, it's only going to change what? X, right? X changes, Y constant. So, line integral from there to there, from this for the moment, I think we're okay with going straight to the integral. So from time at P to time at B along our path of, in fact, let's not even call this thing time yet. So A to P is the piece that you're doing here. It's this one here, right? Oh, very good. We get that. Yes, it should be. Only dependent on A and P, correct. So now we're going to just go straight ahead and parameterize this in the standard way. We're going to go from 0 to 1, right? And we're going to parameterize the line from P to B. The force done at S dot ds dr ds. Right. So I'm taking a dot product here. But now, what direction is the r in all the way along that line? The x direction. So what's going to happen? This is just going to be fx. Fx dot dx plus fy dot dy. But the dy is no dy along this path. Right? You can parameterize it with whatever method you like. But ultimately you're still going to get this plus integral from 0 to 1 fx evaluated at x dx. Right. So let me take the derivative of this word. Let me take the derivative of this word with respect to the n.
And if the is one of the a's in WAB. So that's plus left. Yeah. Large. That A doesn't need error.
Doesn't mean error?
Good point.
Yeah, maybe. Look, the arrow is just to say that A is a point in space. It's a vector. Yeah, I suppose you can take the arrow away. I mean, it's a... Yeah. It's not a reality. Right, so... What have we done? We have worked out an expression, and we're now going to differentiate this thing with respect to x to see what happens. So, in particular, when we differentiate this with respect to x, what happens? Is this dependent on x? No. We very clearly see that it's only dependent on a and p. When we differentiate with respect to x, it's going to disappear. So we now differentiate with respect to x. We now differentiate with respect to x. The value of that work. We're going to get an interesting equation. We're going to get derivative of work from A to B by Lx is equal to 0 plus del by del x of the integral of let me actually parameterize it differently. Sorry, I want to make a particular point. We're going from x0 to x dx. That's just an easier way of saying it. If we write this as the point x0y, and this is the point xy, right? You can quite clearly see that we're going from x0 to x when we do this integral. Now, fx of x from x0 to x dx, we're differentiating something with respect to its upper bound. And that's the other fundamental theorem of calculus, which will tell us that this is in fact equal to simply the value, right? It's simply equal to fx at x. And we can do a very similar thing to show that the derivative of the work from A to B with respect to y is in fact fy.